Creating a Universe, a Conceptual Model. This talk is based on an article published in the Journal of Philosophy and Cosmology. The journal has online access. Einstein once asked the question, how much choice was there in constructing our universe? Stephen Hawking, in A Brief History of Time, responded, there was no choice at all to choose initial conditions, but there would still be freedom to choose the laws of nature that the universe obeyed. This, however, may not really have been all that much of a choice. Our objective, then, how much freedom or fine-tuning is allowed when choosing the laws of nature? The conceptual model provides a framework for this analysis. This is a conceptual model for creating a universe. It separates space, the laws of nature, from energy, initial conditions in plasma, and expansion, the Big Bang process. The Big Bang is dependent on plasma created by initial conditions. Both initial conditions and the Big Bang must follow the laws of nature, which inherently reside in space. Space is something. Space contains the laws of nature, defined in this talk as universal rules, laws of physics, and symmetry. We have significant knowledge about these laws of nature because all our scientific theories assume their presence. Their existence is critical for developing either a unique theory of our universe or a more speculative multiverse. The Big Bang requires an energy source, something to breathe fire into equations and propel the expansion of space itself. The energy source is supplied by initial conditions. Various theories, inflation the predominant one, propose how initial conditions are established. For our universe, each theory produces the same plasma. All the theories are constrained by the laws of nature, which exist in space. Expansion is constrained by both the laws of nature and initial conditions. For our Big Bang, there are just two variables during expansion: initial distribution of plasma energy and randomness in the biological evolution. If the Big Bang occurs more than once, the result is called a multiverse. What supplies the energy for the universe? This chart lists four popular theories that supply the energy. For inflation, the inflatant field. For string theory or M theory, colliding branes. For loop quantum gravity, energy is recycled from a previous universe in a bounce. And for the mathematical hypothesis, it just exists. Although the theories are based on different mathematics and assumptions, they produce identical plasma, a hot, dense energy with specific attributes. Initial conditions establish plasma values for force strength, number of particles, mass of particles, energy density, and entropy. Traditional fine-tuning is the improbable coincidence that these input parameters would produce a universe like ours. Our universe is a rare combination of fine-tuned input parameters. This is why Stephen Hawking said there was no choice at all to choose initial conditions. What happens to the plasma? For our Big Bang, there are just two variables allowed during expansion: initial distribution of plasma energy and randomness in the biological evolution. These independent influences have significant impact, resulting in different universes with different histories, and possibly universes containing no intelligent life or life at all. The first influencing factor is simply matter distribution. With all else being equal, history would vary because different plasma contents, although homogeneous like a gas, are not symmetric. Thus, clustering of matter would vary for each Big Bang. Secondly, the evolution of biological life is also a random, nonlinear process. The sensitivity for biological life is immensely dependent on uncertainties in the microscopic and macroscopic level. As Paul Davies said, to sum it up in a phrase, life as we observe it today is 1% physics and 99% history. Thus, there is no assurance of duplicating our form of life. What we can safely predict from identical plasmas are the physical attributes of a universe: atoms, gas clouds, stars, black holes, and galaxies. This is because the laws of nature treat two identical plasmas the same. With this overview of energy and expansion, we are now ready to analyze the laws of nature. Space inherently contains the laws of nature. Although the ultimate source for space may always remain unknown, we define space as an abstract reality that just exists. Each of these laws of nature are required for our universe. For example, if there were no quantum mechanics, the atom would not exist. This is a significant obstacle. Scientists generally ignore speculating about different laws of nature because they are what they are, and because visualizing different laws of nature challenges the imagination. Only the hypothetical multiverse theory proposed by Max Tegmark entertains different laws, and even then, a vivid imagination is insufficient to visualize the consequences. By considering options for the laws of nature, we will discover that our universe is even more unique than predicted by traditional fine-tuning. Our first law of nature is the universal rule, mathematics. Observed patterns of nature are explained by mathematical equations. As Brian Greene said, monumental upheavals in physics have emerged time and again from vigorously following mathematics' lead. For example, equations Maxwell's, Einstein's, Friedman's, and Schrödinger all fall into this category. So what is the alternative? Must the laws be mathematical, or is there another option? Brian Greene again addressed this issue. I can imagine an alien encounter during which, in response to learning of our scientific theories, the alien remarked, "Oh, math, yeah, we tried that for a while. At first it seemed promising, but ultimately it was a dead end. Here, let us show you how it really works." Greene continues, "I don't know how the aliens would actually finish the sentence. I'm not even sure what kind of answers wouldn't amount to math." There are a number of mathematical structures describing different types of space. Typically, we relate to Euclidean three-dimensional space, but special relativity introduced time, a fourth dimension, for Minkowski space. Then, general relativity added Riemann space, allowing curved space-time. Then, quantum mechanics defined Hilbert space, an abstract, infinitely dimensional space where the wave function lives. For our universe, the number of effective dimensions of space must equal 3. With fewer, there is insufficient gravitational attraction. A universe where 1 or 2 space dimensions would be bland and lifeless. With more than 3, there are also no stable atoms. String theory proposes 10 space dimensions with 7 compacted and undetectable, leaving 3 effective dimensions corresponding to what we observe. This chart shows properties of the 3 standard model of particle physics forces, along with the gravitational force. We will consider space-time distortions of force. The forces function over distances in dissimilar ways. The strong force strength increases with distance, but only acts over an extremely short range. The weak force also acts over a short range, but decreases with distance. The electromagnetic and gravitational force strengths decrease inversely with distance squared, but have unlimited range. Their strengths are set by initial condition theories, and in our universe they vary enormously. The forces are very different, yet it is amazing how they work in harmony to produce atoms and galaxies. Fields. According to quantum field theory, a field occupies space and contains energy. In addition to fields associated with forces and particles, 2 other unique fields exist in nature. The Higgs field, permeating all of space, is responsible for particle mass. It does not dilute as space expands, a characteristic shared with the dark energy field, also referred to as the cosmological constant. Also, if the inflation theory is correct, the inflaton field would exist. Particle species. In quantum field theory, particles are defined as disturbances in fields. In our classification, elementary particles are either fermions or bosons. Fermions are subject to the Pauli exclusion principle. 2 fermions cannot occupy the same state at the same time. Bosons are the force carriers. They are not subject to the Pauli exclusion principle. Protons and neutrons are baryons. baryons are created with combinations of 3 up and down quarks. Our universe needs electrons, neutrinos, which are integral to nuclear reactions, bosons, and baryons. Are the other quarks and leptons required? Laws of thermodynamics and electromagnetism. The 4 laws of thermodynamics are listed. The second law, the tendency of physical systems to evolve towards higher states of entropy, plays a critical role in the evolution of a universe because it dictates a low entropy at the start of the Big Bang. A high temperature corresponds to more symmetry and a simpler system with more order and low entropy. Thus, as time advances, entropy increases and the universe becomes more disordered. In some fundamental sense, all systems are trying to obtain thermodynamic equilibrium. Laws of electromagnetism express relationships among electric and magnetic fields and the distribution of electric charge and electric current in space. These laws explain all of chemistry and biology. What would happen if any of these laws were modified or replaced? Continuing with the laws of nature. Special relativity limits the velocity of light by establishing a maximum speed limit for energy and matter. Approaching the speed of light, mass increases, time dilates, and length contracts. The equivalence principle equates the force of gravity and the force of acceleration. This surprising relationship was proven by general relativity. Einstein's equations unified space, time, energy, and gravity. As John Wheeler once said, matter tells space-time how to curve, and space-time tells matter how to move. There is no way to hide from gravity. Quantum mechanics is required to construct atoms. As Richard Feynman describes them, little particles that move around in perpetual motion. In Newtonian physics, an accelerating electron loses energy. Thus, an electron traveling at about 1/10 the speed of light spirals into the nucleus. Quantum mechanics solves this problem by providing 1. Probability waves to replace electron circular orbits, 2. The Pauli exclusion principle to assure the discrete electron orbits, and 3. Discrete energy states reflecting multiples of Planck's constant. This allows electrons to move from one energy state to another, generating or absorbing photons. These clever concepts allow atoms, elements, and molecules to exist. How about entanglement? Does transcending space and time, non-locality, provide an integral function? It might be expendable for our universe, but are we sure? Symmetries are the foundation from which laws spring. Frank Wilczek emphasized this point. The study of Maxwell's equations brought out an essentially new idea that had not played a role in science before. That is, the idea that equations, like objects, can have symmetry, and that the equations nature likes to use in her fundamental laws have enormous amounts of symmetry. For time, space, and motion, the conservation laws associated with symmetry are called Lorentz symmetries. The standard model of particle physics includes more abstract gauge symmetries denoted by mathematicians as U1, SU2, and SU3. Strange as it may seem, selective symmetry breaking is allowed. At least 2 of the 4 forces, the electromagnetic force and the weak force, are subject to symmetry breaking at extremely high energy densities, temperatures of about 10 to the 15.5 degrees K. Above this temperature, the forces function as one, the electroweak force, demonstrating greater symmetry. One of the unsolved puzzles of cosmology is the asymmetry or violation of baryon number. Symmetry that states baryons and antibaryons are created and destroyed in pairs. If perfect symmetry prevailed, only radiation would exist. Without this violation of symmetry, there would be no matter. So, selected laws of nature are not always absolute. It appears they occasionally allow discrepancies. The multiverse. Assuming more than one universe, this graphic shows the consequence of different plasmas and different laws of nature. Earlier, we talked about the Big Bang variables and one or many universes depending on one or more Big Bangs. This scenario is the top two lines. The next scenario produces a different plasma via other initial conditions. Plasmas with different parameters produce a universe with different physics, or it may produce something bizarre, an undefined universe, or many undefined universes. The last scenario on the bottom, with different laws of nature, implies multiple versions of space, each with its own assortment of laws of nature. For example, space might contain 3 rather than 4 laws of thermodynamics. However, if either laws or initial conditions differ, all bets are off for a stable universe. Visualizing different laws of nature. Our model does not attempt to prove or disprove the controversial multiverse theories. It supports a unique theory for our universe, one mathematical solution, or multiverse theories. It is conceptual analysis identifying all possibilities. Visualizing different laws of nature may be beyond human comprehension. Take, for example, Max Tegmark's explanation of mathematical structures, quoting, "In some mathematical structures, there is no light. In others, there is no gravity. Going still more radical, there may be many mathematical structures that do away with space and time altogether, so there is no meaningful sense in which anything is happening in them." End of quote. If you have no light, do atoms exist? If there's no gravity, what then? A universe without space or time challenges human comprehension. Speculation may be more philosophy and metaphysics than physics and cosmology. Does reality consist only of our observed laws of nature? We may never know. What has the model accomplished? First of all, it categorized the laws of nature as universal rules, laws of physics, and symmetries. Second, it separated the Big Bang from initial conditions. Third, it positioned traditional fine-tuning within a larger framework. Fourth, the proposed model encompassed both the unique universe and the multiverse possibilities. And fifth, it validated that when creating our universe, there was virtually no choice for the laws of nature. They are what they are. Please reference the source article for additional detail. Thank you.